Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last few classes, we basically looked at a lot of schemes for finite difference. We solved some problems also, starting from model problems like the convection equation, convection diffusion equation, nonlinear equations, and also some practical problems like the sock tube problem, right? And we saw how different schemes behave in different scenarios, what is the requirement of the CFL number, the time step, okay, and which schemes are more dissipative, which schemes are dispersive, and so on and so forth. And today's class we are going to begin a little bit about the introduction of the finite volume. We will not go into the great detail, but I will give you a flavor so that you will understand what really happens in a finite volume code. So, if you look at most of the popular codes in CFD, which are either commercial or open source, they are mostly based on finite volume. For example, Fluent, OpenFOAM, and then star CD, star CCM plus, and then you have CFD plus plus. So, many codes. Okay, in India also we have codes like hyphen 3D. Okay, and then geosymmetrics has got some codes. So, most of these codes are basically based on finite volume, and there is a reason behind it. So, the finite volume basically allows you to basically keep different kind of mesh elements. For example, if you I mean, for example, what we have seen till now, that if you want to use finite difference, you have to have a grid which for which you should have the information of I minus 1, I minus 2, I minus 3, and similarly I plus 1, I plus 2, and I plus 3, and so on and so forth, right. So, it is a kind of structured grid. It may be uniform, that means your delta x is constant, or it may be non-uniform, that delta x is varying. Okay. For example, if you want to solve the boundary layer, you will have the stretching in the grid. Your first grid point will be very close to the wall, and after that it will slightly increase, and as you go towards the far field, your grid size will increase. So, that is a non-uniform grid, but still it is an structured grid. Let us say if you try to fill the same domain with an unstructured grid, you will have difficulty using the finite difference approach. Why? Because you are losing the information about the connectivity of the nodes. Okay. So, if you want to use any difference formula, okay, let us say the upwind scheme, the fourth order schemes, or even the compact schemes, Lax-Frederick, any kind of scheme that you want to use, you will have difficulty there. Okay. On the other hand, if you use a finite volume, you can use grids which are grid elements which are of different kinds. You can have a, let us say, triangular grid element, or you can have the quadrilateral in 2D. In 3D, it can be a hexahedral, or it can be a prism. Okay, many different kind of elements you can use, and this will all work in finite volume. So, in other way, if I want to put it, the finite volume can support very complicated domains, okay, very complicated geometries. Let us say if you want to simulate flow over an aircraft, which is where the design is very complicated. You have got fuselage, you have got wings, you have got slats and flaps, everything deployed. You have got ailerons, you have got all those basically control surfaces, everything deployed, okay, and you want to simulate it, right. So, of course, you cannot use finite difference in that particular case, right, because you cannot put a structured grid there, right. It is very difficult. Okay. Even if somehow you are able to manage it, it will take you, I mean, inordinate amount of time just to create a grid. Okay. So, in those cases we basically try to go for the finite volume approach. So, let us look at some of the basics of the finite volume approach. Okay. So, I mean this is the basic equation in 1D I am writing. So, del U by del T plus del I by del x equal to 0. Okay. And you can see that this represents your this can represent any equation that you want. Okay. It can be a convection equation there f equal to just a Cu. Okay. It can be a diffusion equation where you are basically putting the double gradients inside this function f. Okay. So, basically f equal to maybe k dt by dx or something like that, right. So, it can represent we have, as we have seen, it can represent the 1D Navier-Stokes equation also, okay, where the f can be basically f I plus f v, okay, the inviscid part and viscous part. Okay. So, this is a general equation. If you want to go to multidimensional, same thing will become del u by del t plus del f by del x and plus del g by del y. If you want to go to 3D, then this will be del s by del z. Okay. But idea is same, right. So, you have a time derivative term and you have few surface derivative term. Okay. In fact, you can write this entire thing as del u by del t plus del dot f, okay, equal to 0, where f is basically now is a vector which consists of f, g and h, right. So, we will see that this form is very useful when you want to cast a finite volume. Okay. Now, when you basically discretize the equation as it is, like you have this differential form and you discretize it. So, then what you get is a finite difference approach, right, because as if you recall this del u by del t is nothing but u I n plus 1 minus u I n by delta t and del f by del x depending on what scheme you are using. If you are using a backward scheme, so this is f I n minus f I n minus 1 by delta x, right, and just put both this into this equation 1 and you can basically write a discretized form equation where u n plus 1 I is a function of u I n, right, and it will have delta t, delta x and all those things which are governed by your CFL law. Once you fix the grid, you will look at the Courant condition, CFL condition, fix your delta t and you can solve it, march it and solve it. If it is a implicit problem, implicit scheme, for example, you are using Euler backward for example, then it will become u I n plus 1 is equal to f u I n plus 1. Okay. So, basically it will be a matrix which you need to invert and solve it. Okay. This is an implicit form. Okay. So, in that case this will be, okay, this is f I minus 1 n. Okay. If it is in implicit scheme, this is f I n plus 1 minus f I minus 1 n plus 1 and delta x, right. So, remember top we are putting this one is for time and this one for space, right. So, basically we are not altering the equation, we have the equation. Okay, we are solving the differential form as it is and we are getting our discretized equation which we solve. We can time march it or maybe put in a matrix form and solve for basically the next time step, right. In the finite volume, you basically do not need a structured mesh. So, let us say if you want to solve the problem that we had earlier. Okay. So, in 1D you are basically solving I plus 1, I minus 1, I minus 2 and I plus 2 and so on and so forth, right. If it comes to 2D, you will have a mesh like we have been discussing, for example, case of the lid driven cavity. Okay. So, you will have a mesh which is like kind of nice and structured, right. It is only the dimensionality which changes. Okay. So, now you have only instead of only I, you have I and j, right, but still it is structured. Okay. And you have information about all the things, right. So, this is, let us say this is I and this is j, right. What if I want to basically put very complicated domain here, right. So, or let us say on the same domain you are putting a very complicated grid. Okay. Let us say I want to use a grid which is something like this. Okay. okay, something like this. Okay. They are, of course, they have to connect to the boundary, okay, but this is my grid. Okay. Okay. Of course, they are non overlapping elements, it needs to be non overlapping, one element cannot overlap another. Okay. So, you cannot use the finite difference scheme in this one. Okay. So, on top you can use this finite difference scheme here, okay, but if you want to solve the bottom one, okay, you have to use the finite volume scheme. Okay. Now, you can see that while making it, I put some quad elements here. Okay, this looks like a quadrilateral. Okay, and then you have many triangular elements. Okay, for example, this one is a triangular element, and so many, right. So, one thing you would note here is that all these, if you see, so all these elements you can basically imagine that these are kind of cell. Okay, and this all these cells we have a cell center here. Okay, let us say this is a cell center, and then you have basically different edges. Okay, for each cell, maybe it is quadrilateral, then there are 4 edges, okay, or you can call it 4 faces. If it is a triangular, then you have 3 faces. Okay, then also you have a cell center, okay, and then you can have basically 3 faces here, right. Similarly, you can have pentagon. Okay, if you you can imagine in 3D, then it can be a basically hexagonal element or a prism element, okay, or many different kind of elements, whatever you can imagine you can put it there. All you need is a cell which has got different number of faces. Okay. So, before going into the formulation of finite volume, let us define some terminology. So, in all these cases, this the one in the center is called the cell center, which is basically shown here. Okay, this is your cell center. So, this entire thing is your cell, every element that you see. So, here it is shown in a very nice form, but you do not have to be so nice. Okay, the grid does not have to be so nice, it can be very complicated also, and still you will have a definition of a cell, where at the center, okay, you will say that, okay, this is my cell center, and then I have 4 faces. Okay, 1, 2, 3, 4. Okay, each cell will have faces, and then basically these are the nodes. Okay. Now, what happens? There are different approaches in finite volume also. So, some are called the vertex centered. There are 2 approaches basically, one is the cell centered and other is vertex or node centered. Okay. So, in the cell centered approach, you will have variables stored at the cell center. Okay. This is okay, these are my cell centers, where our variables, for example, your conserved variable or primitive variable, they are stored here. Okay. In the vertex centered or node centered approach, you will have the variables which are stored at the nodes. Okay. So, then if you want to make a grid there, okay, this will be your cell. Okay. If I take this node, this is my cell. Okay. So, similarly, you can collect each node there and you can make a cell around that. Okay. So, that is just the way you do it. So, for example, if I take this structured grid, okay, so this could be my cell center. Okay, everyone I have got the cell. So, this is my domain. Let us put the very nice boundary conditions. Okay, so you have wall everywhere. Okay, and let us say right top one is a moving wall, but still it is a wall. It is a moving wall which is moving in the right direction. Okay, so in the cell centered approach, you have the values everywhere here, okay, at the cell center. In the vertex centered approach, if you use, so you will have values here, okay. Okay, but you have to create a cell around that vertex. Okay. So, that is very, very important. So, in this class, we will discuss about the cell centered approach. Okay, vertex centered is also not very difficult. It is the way you have to basically imagine how you are going to make a cell around each vertex, but even around vertex you will have basically cell and you will have faces in that cell. Okay. So, in the cell centered approach, for example, if you look at this cell, okay, if you look at this cell, it has got 4 faces. Okay. So, this is a nice quad mesh. Okay. But as I have been telling, you do not have to be have very nice mesh. Okay. Now, if you to simplify it, let us look at the 1D domain. Okay. So, like the one you solved for the short shock tube, remember what we did for the short shock tube problem. We had a length of let us say 1, and we discretized into let us say 101 points. Okay. And 1 to 51 we use some boundary conditions, not boundary condition, initial conditions. U was 0, P was 1, rho was 1. Okay. On the right hand side we had used the initial condition u equal to 0, P equal to 0.1 and rho equal to 0.125. Okay. So, this was our short shock tube. Okay. So, this was, if this is I, this is I equal to 51, this is the midpoint. Okay. And then this is I equal to 50, I equal to 51, and so on and so forth. Okay. And we had boundary conditions at 101, right. If you want to solve this using a finite volume approach. Okay. So, here in finite dimension it is very simple, we had this I plus 1, I minus 1. Okay. We basically got the derivative for del u by del x. Okay. And basically we use our favorite scheme. For example, you can use the Lex favorite scheme to approximate the entire equation to get the discretized form, and just basically keep on marching it. Okay. If you want to solve it using the finite volume approach, okay, what you would do is basically you may have 101 points, but in all these 101 points, okay, okay, so this is 2, this is 3, this is 4, this is 100, this is 99. Okay. So, you will start creating cell centered. Okay. So, between the two edges or two faces, if I can call it here. Okay. So, you will have a cell center here. Okay. This is I, around I you will have faces here, and then you will have I plus 1 and I minus 1. Okay. Immediately see that the number of cells that you have is equal, actually in 1D case it is 1 less than your number of edges. So, if it is 101 number of faces, with 2 faces you have got 1 cell, this is 1, 2, 3, okay, and then you have basically 99 and 100, right. So, using the same terminology, so this is my cell. Okay, because this is my cell. Okay. So, these are my cell faces. Okay. And we can further simplify it, we can call this is between cell I and I plus 1. So, we can call this I plus half. Okay. This is my face. Okay. And similarly, this one I can call it I minus half, this is my another face. Okay. For 1D each cell will have 2 faces, okay, left and right. Okay. In 2D depending on what kind of elements you are using, you can have 3 phase or you can have 4 phase, okay, you can have 5 phases also in 2D. Similarly, in 3D depending on what kind of elements you are using, you will have 6 phases, 5 phases, and so on and so forth. Okay. Now, for each cell you will define something called cell volume, represented by omega I. Okay. So, this is basically the area, okay, of the cell. So, in 2D it is the area, because your 2D representation of the cell is like this. In 1D it is just the distance. Okay. So, let us say this is 1D, this is delta xi is my cell volume. Okay. I am using the terminology which is basically used for the 3D, because it is easy to basically imagine it when you go to 3D. So, for example, in 2D it is the area, okay, in 1D it is distance, and in 3D if you go it is like the volume, okay, cell volume. Okay. So, because we call it cell, so we will use this terminology volume everywhere. Okay. So, in 1D case this omega is just nothing but delta xi, that is my cell volume. Okay. Basically the distance from face to face. In 2D let us say this is my delta xi and this is let us say delta yi. So, my area will be delta xi delta yi. Okay. In 3D it could be delta xi, delta yi, delta zi. Okay. And there are many approaches to basically calculate the cell volume also. One thing you need to make sure that your cell volume cannot get negative. Okay, if your cell volume is going negative, then there is some problem in your calculation. Okay. So, we got the definition of the cell center, cell faces and the cell volume. Okay. Now, let us see that how we are going to use our finite volume. Before that, just a quick recap. Okay. So, del U by del T is defined using your forward in time. This is right now it is forward in space. So, this is FTFS scheme, and you got a scheme which is for uniform grid, which is like this. For non uniform it is delta xi. Okay, very simple. In finite volume, what we do? We are going to solve the integral form. Okay, and this is also called the weak formulation. Okay. So, basically what we are going to do? We are going to integrate the equation around each cell. Okay. Again, remember this picture. Okay, this is my cell, this is I, these are the faces, this is I plus half, I minus half. Okay. And then you have cells here, I plus 1, I minus 1, and this is my omega I. Okay. Remember this picture. So, what we are going to do? We are going to basically integrate our equation. So, our equation is del U by del T plus del F by del x equal to 0. Okay. In finite difference, we solve it the equation as it is. You discretize all both of these, use your favorite scheme and solve it. In the finite volume, we are going to integrate it around its cell. Okay. So, let us integrate this equation. We are going to integrate it from, let us say, because we are solving from if we are talking about this cell. Okay. So, it goes from I minus half. So, you can call it x I minus half to x I plus half. Okay, and then it will become dx, okay, equal to 0. So, you are basically integrating the value around each cell. We can separate this out, and it will become x I minus half, x I plus half, okay, and du by dt, okay, and plus this would be dx, okay, and plus x I minus half, x I plus half del A by del x dx equal to 0. Right. Now, what we are going to do? We are going to define a cell average quantity. Okay. That means, what we are saying that the value that is the cell center, that is residing the cell center, is the average of the value. So, your u may have variations from I minus half to I plus half, right, but we can take an average of that. So, whatever variation you have. So, let us say I have u at dx, some variation you have I minus half to I plus half. Okay. You integrate it from this to this and divide by the basically the area of this delta x, and then it will give you the average value, right. So, if you replace this in this equation in the first term here, so what you will see that your dependency on x goes away, right, because you are using a cell average quantity, right. So, right now you have integration with respect to x, and then you have del U by del T, right. So, if you can define a cell average quantity, then what you can write this equation as du bar by dt, right, and then you will have this one you can see that this is dx and dx. So, this will become f I plus half, which is nothing but the flux evaluated at I plus half, okay, minus f I minus half is equal to 0. See what we did, we took a differential form, integrated in the cell, okay, and I am showing it for the I, but we are going to do it for every cell, and this is the final form that we are getting, okay, del by del T plus f I plus half, f I minus half equal to 0, right. So, this f I plus half and f I minus half are nothing but the fluxes, okay, at the interfaces, okay. So, these are my interfaces or cell faces, whatever you want to say, okay. So, something is coming in and something is going out, right. So, if you want to understand it in a more physical sense, so what is this du by dt? Basically the change in value with time, right. And what you are saying that this change in value is basically equal to whatever thing that has gone out minus whatever thing that has come in, right. Because this is a plus sign, if it is minus sign, this is basically the generation, that is whatever came in minus whatever went out, right. So, these are the flux quantities f I plus half and f I minus half. Okay. So, now we have removed the spatial dependence. Okay. So, here I have used the delta x I earlier. Okay. See, yeah, there will be delta x I here. Okay. Because del U by del T is defined, I mean this will be u bar delta x, right. So, that is nothing but your cell volume. So, your omega I del U by del T I is equal to f I plus half plus f I minus half equal to 0. Now, once you will notice here that as soon as we define the cell averaged quantity, okay, what we did is we converted our PDE to ODE. Okay. That means, if you can somehow find the fluxes at I plus half and I minus half, okay, all you need is a time discretization scheme to solve this du bar by dt, okay, or we can write it in this form, right. You know the cell volume, this is a geometrical parameter, you define a cell, you define a cell volume, okay, you have the fluxes, okay, I plus half and I minus half, just subtract it, and you can use any favorite scheme that you want. You can use Runge-Kuttai scheme, Euler forward, Euler backward, whatever scheme you want, Adam-Basforth, okay, and you can just solve it. Okay. So, this is how your final, this is called the state update formula. Okay. Why it is state update formula? Because you are updating to n plus 1 from the value n. Okay. Using the same principles that we had for the finite difference, let us say you do it for n plus 1 here and n plus 1 here, that becomes an implicit scheme, right. But let us stick to the explicit scheme here. So, that this right hand term is called the RHS, the right hand side term is called the residue. Okay. So, if you use fluent or many different solver, you would be looking at the term that how the residue is going down, right. So, basically you say that if it has gone down to 10 to the power minus 4 or minus 5 minus 6, then your basically solution is converged, right. So, that means what is happening there, okay, let's understand here. So, this right hand time, this entire right hand term is my residue, okay, this is my residue or residual, okay, the different terms which are being used in different literature. Okay. So, if the problem is steady state and you say that my residual has gone down to 10 to the power minus 6 or let us say 10 to the power minus 7, sometimes 10 to the minus 10 also, that means the value is very small. It is small enough that we can say that this my value du bar by dt is basically approaching 0, because the value is very small. That means you have reached the steady state, right. You can also think that if the flow problem is steady state, that means my mean flow is not changing, then why you care about this du by dt? You can remove it directly and solve it here, only solve the right hand side part. If you want to do that, you can try that and you will see that you will quickly realize that you are not getting converged solution, okay, because you will put some initial condition which may be very different from your mean solution, and it does not have a direction how it go to basically the converged solution. If you use this time marching scheme, okay, where you have this on the left hand side, okay, you can see that you can keep on measuring the residue, and as it goes to a very small value, you can say that my solution is converged. But this is for only steady state. If it is unsteady, okay, then you know that my del U by del T is not 0 here. Okay. So, still the definition remains the same, you have got the residual and you have got the time dependent term on the left. So, this is our final state update formula. You can calculate the n plus 1 with respect to n, and if it is a uniform structured grid, then you can basically use this omega I, because if it is 1D flow, for a 1D flow, this will become like this. Okay. I will show you that for a structured uniform grid, the finite difference and the finite volume are the same. Okay. The formulation may look very different, but if the it is 1D uniform structure grid. Okay, you can basically show it that the both the schemes are same. Okay. Now, what are the things that are remaining? So, we have defined our state update problem very well, okay, but what are the things that are remaining? One thing is that you want to calculate the Fi plus half and Fi minus half, right. So, basically how what are the value of flux here and here. Okay. So, Fi plus half and Fi minus half. Okay. So, how do we calculate? You know, you are using the cell average value which is ui here, but you want to calculate the fluxes at the interfaces. Okay. So, what are the considerations? What are the basically requirements that you have to impose to calculate those fluxes? That is one problem. Second is how does this u vary inside this volume? Okay. So, you have this volume and you have this cell center value, but you have the variation of u inside this, right. So, how does it vary? So, these are the two questions that we need to answer, and we will discuss this in the next class. For now, remember that we need the interfacial fluxes, okay, to calculate the value at the next time step. Okay. And if we have some way we can calculate the interfacial fluxes correctly, the method is very easy. Okay. You will calculate the right hand side term, the residual term, and use our favorite scheme and get the next state update. Okay. So, with that we will stop here and we will meet in the next class. Thank you.